Hi, we're going to look at solving this differential equation. So the first thing you want to do anytime you solve any differential equation is be sure you know what kind it is. So you're going to classify it according to order, linearity, etc. So this one you should be able to see pretty easily is a second order linear non-homogeneous differential equation, and so that provides us some direction in how we're going to solve this. So we're going to be looking for a solution of the form y equals y sub h plus y sub p, where y sub h is a solution to the homogeneous differential equation associated with this differential equation, and yp is a particular solution that satisfies the non-homogeneous differential equation. Alright, so we're going to start by finding yh by solving the associated homogeneous differential equation. And if this were a constant coefficient differential equation, that would be pretty straightforward. This one is not. The coefficient functions are variable functions, and so there are several different ways that we might explore throughout the rest of this course for solving that. This one, however, is of the form where you might think about that a reasonable guess for the solution is that the solution is going to be some power function. So y equals t to the m, where m is some specific power. If you just look at the form of this and think about taking derivatives, and the derivatives multiplied by t squared and multiplied by minus 2t, and then the original function multiplied by minus 4, all those are going to have to add up to 0. So you're going to have lots of cancellation. So you might guess that the solution is of this form t to the m. And so just as we've done with several different methods, we're going to make that guess, we're going to make some substitutions, and see what is the value of m that makes this work. Alright, so I've substituted in my y double prime and my y prime and my y guess into the associated homogeneous differential equation. And now I'm going to go ahead and simplify and see what values of m are going to work here. Okay, so when I simplify using exponent rules here, my t squared and my t to the m minus 2, when I add those exponents, I just get t to the m. And then same thing on the next term, a t times a t to the m minus 1, and when I simplify that, I also get just a t to the m, and then I've got a t to the m in my last term. So I have this common factor of t to the m that I can go ahead and factor out. And we want this to be true in general, not just for a specific value of t. So this is only going to be true if t to the m is equal to 0. There is no value of m that will make t to the m equal to 0 for all values of t. So we're going to not focus on that, and instead we're going to focus on what I have in the brackets here, m times n minus 1 minus 2m minus 4 equals 0, and find values of m that make that true. So m equals 4 and m equals negative 1 are the two m values that make that true. So remembering that my m was the exponent in my initial guess for y equals t to the m as a solution to this differential equation, this work indicates that y equals t to the 4th and y equals t to the negative 1 would be solutions of the associated homogeneous differential equation. We could verify that we didn't make any mistakes in our algebra by taking appropriate derivatives and substituting into that homogeneous differential equation. The other thing that's relevant is knowing that we have a second order linear homogeneous differential equation at this step indicates that we need two linearly independent solutions to build the general solution for our yh. So these are obviously linearly independent. There are several ways to think about that. One is, since I have only two of these objects, linear independence comes down to thinking about one of these as a scalar multiple of the other. And you can think about those in terms of functions, maybe function graphs, understanding that this t to the 4th function and t to the negative 1 or 1 over t function, the only time those would be scalar multiples of each other would be if the scalar is 0 and they both become the 0 function. You could also use a Wronskian or the definition of linear independence to show that those two functions are linearly independent. So YH is going to be our linear combination of these two linearly independent solutions to the associated homogeneous equation. Then for the YP, I might think about different ways to do that. So the method of undetermined coefficients, if you sort of think through that and think through this right-hand side function and all of its derivatives, you'll notice that that does not form a finite list. If you think about just taking derivatives of t to the negative 3, you just keep going and going and going. You never get back to the same functions. So I'm going to use variation of parameters to find that YP. In order to use variation of parameters, I need the differential equation to have a lead coefficient of 1. So I'm going to divide my original differential equation through by t squared. That is not going to affect my YH solution. That's a solution to the differential equation, in the homogeneous differential equation in either form, so that's okay. But in order to use variation of parameters to find my YP, I need my differential equation to have a lead coefficient of 1. So I'm going to go ahead and rewrite the differential equation dividing through by t squared. Alright, so here is my non-homogeneous differential equation that we are going to solve using the method of variation of parameters. So when we do the method of variation of parameters, we're going to solve a system of equations. And here's our system. So our y1 and y2 are going to come from our homogeneous solution. So I have these up here near the top of the screen. There's my y1 and y2 from my associated homogeneous equation. And our f of t is that function on the right-hand side of the differential equation, 1 over t to the 5th. So I'm going to go ahead and write down that system of equations with our appropriate functions plugged in. Alright, so this is the system that we're going to go ahead and solve. So there are a lot of different ways to solve this. I'm going to go ahead and isolate u1 prime in the first equation, substitute that into the second equation, and go from there. Okay, so in the first equation, when I solve for u1 prime, I got negative u2 prime times t to the negative 5th. So I'm going to substitute that into the second equation in place of u1 prime. And then solve for u2 prime. So we want to be careful with our algebra there. Just make sure you're clear when you're dividing, when you're adding and subtracting, and make sure you're clear about those exponent rules you're going to use to simplify that. There's my u2 prime, and what I really want though is u2. So I'm going to go ahead and integrate with respect to t to find that. We can neglect the plus c here because of how we're going to use this in forming our YP solution. Now that I've got my u2, I want to go ahead and find my u1. So I'll go back to my work in my system, and I'm going to substitute my u2 prime into the equation I just highlighted, and then use that to find u1. Make sure you substitute in u2 prime and not u2 in place of u2 prime. So I've got u1 prime equals 1/5 t to the negative 8. So I'll find u1 by integrating that with respect to t. Okay, I've now got my u1 and u2, so I can use that to find my yp. So the tricky thing here is just making sure you put all the right things in the right places. So this is where it's important to make sure you've labeled your work properly. So u1 times y1, so I'm going to go way back up here. My y1 was t to the 4th, and my u2 was 1/10 t to the negative 2, and then going back up here to look at my y2, that was t to the negative 1. I do get some nice simplification on this one. Okay, so there's my yp, and then that allows me to write my general solution to the original differential equation, y is going to be yh plus yp. Alright, so there is my general solution to the original differential equation. We could verify that this is indeed a solution and that we haven't made any mistakes by taking appropriate derivatives and substituting into the original differential equation.